When an artery is blocked, the body cells it supplies becomes injured because of the lack of blood. This injury can progress to cause cell death, a process called infarction. If this occurs in the coronary arteries, the heart muscle, called the myocardium, will start to die. This event is therefore known as a myocardial infarction, more commonly known as a heart attack. The myocardium cannot regenerate. Instead, the heart develops scar tissue. This permanently weakens the heart's pumping ability, which over time can ultimately lead to heart failure. Once the myocardial infarction is treated, drugs are given for life to help support the heart and slow the development of heart failure. The key drug classes we give include antiplatelets, RAS inhibitors, cardioinhibitory drugs, and statins. Antiplatelets are given to prevent future clots from developing in the arteries. These are what cause the myocardial infarction. The chemistry of these drugs has been discussed in a previous video, and so the rest of this video will focus on the other drugs. Statins are drugs to help lower the amount of cholesterol in the blood, and specifically lowers a cholesterol particle called LDL. LDLs are what make the atherosclerotic plaques, which are what narrow the coronary arteries and rupture to cause the clots. Statins achieve this by blocking the enzyme HMG-CoA reductase within the liver. This is an enzyme that converts HMG-CoA to substrates that ultimately form cholesterol. As the cholesterol level falls, the liver senses this and upregulates LDL receptors. This is to scavenge more LDLs to help produce more cholesterol. The overall effect is therefore a reduction in LDLs. The structure of all statins includes a HMG moiety, which is what binds to the active site of the enzyme. The amino acids in this active site, known as the cis loop, form polar interactions with the HMG moiety, including dipole-dipole and iron-dipole bonds. A lysine residue also forms a hydrogen bond with the proximal hydroxyl group here, and another lysine residue also forms a salt bridge with the carboxylate group here. A salt bridge is the intermolecular force between a hydrogen atom and an anion. The two groups are sufficiently close for hydrogen bonding, but not enough to create an ionic bond, hence forming a sort of bridge between the two bonds. Whilst the HMG moiety occupies the active site, the rest of the statin is then kinked at this proximal hydroxyl group to point downwards towards the opening of the enzyme. The bulky groups thus sterically inhibit entry of any further HMG-CoA. Statins also possess pleiotropic effects, that is, non-lipid related effects, which also reduce cardiovascular disease. This explains why statins are known to be beneficial in people with normal cholesterol and no prior history of cardiovascular disease. This is because the intermediate products of the cholesterol pathway help modify various proteins. Without these proteins, this affects the production of inflammatory messengers, such as interleukin-6 and CRP, and it slows the breakdown of beneficial messengers, such as nitric oxide. We'll revisit nitric oxide towards the end of the video. The renin-angiotensin-aldosterone system, or RAS, is a hormonal system that works to maintain the body's blood pressure through vasoconstriction of arteries and absorbing more fluid in the kidneys. Following a myocardial infarction, the heart struggles to maintain the blood pressure, and so the RAS activates. Unfortunately, this compensatory process becomes excessive, and the excess blood volume and higher pressure puts strain on the heart, causing further myocardial injury. As you can see, a vicious cycle starts to develop that ultimately pushes the heart into heart failure. RAS inhibitors therefore stop this system and dampen the progression to heart failure. The key messenger in this system is the angiotensin II protein, as it coordinates all the effects of RAS. The angiotensin converting enzyme or ACE, converts angiotensin 1 to the active form angiotensin 2. ACE inhibitors are drugs that inhibit this enzyme and stop the production of angiotensin 2. The active site of ACE contains a zinc metal ion, and ACE inhibitors work by binding to this ion. Old inhibitors, such as captopril, contain a sulfhydryl group which forms a dative covalent bond to the zinc ion. Newer inhibitors, such as ramipril and lisinopril, contain a carboxyl group. This dissociates to form a carboxylate ion, which also forms a dative covalent bond to the zinc ion. Although both inhibitor moieties form covalent bonds, the sulfhydryl group forms a stronger bond than the carboxyl group. This is because sulfur is less electronegative than oxygen, causing a greater sharing of electrons. However, the newer inhibitors also contain phenyl groups near the carboxyl group. These phenyl groups are hydrophobic in nature and bind to hydrophobic amino acids at a neighboring docking site. This docking site is crucial to stabilize angiotensin 1 into the active site. Because of this additional effect, the newer inhibitors are more potent. Another RAS inhibitor is the angiotensin receptor blocker, or ARB. These inhibit the angiotensin receptor that angiotensin 2 binds to, thus preventing its effects from manifesting. These drugs are used as an alternative to ACE inhibitors.
ARBs contain tetrazoles. A tetrazole is a pentagonal aromatic ring containing 4 nitrogen atoms. This tetrazole
protonates either an arginine or lysine amino acid in the active site, thus forming a salt bridge between it and the positively charged amino acid residue. Newer ARBs also possess a carboxyl group that helps make further salt bridges. The potency of ARBs is therefore determined by the number of salt bridges. Inotropy is the force of contraction of the heart, whilst chronotropy is the rate of contraction. Cardioinhibitory drugs decrease either the inotropy, chronotropy, or more typically, both. Following a myocardial infarction, because of the weakened ability, the heart pumps harder and faster. However, this increases the oxygen demand on the heart muscle. Therefore, whilst it sounds counterintuitive to decrease the heart's pumping ability, it helps to limit further injury to the heart over time. The main class of cardioinhibitors we give are called beta blockers. These are drugs that inhibit beta-1 receptors in the heart. These receptors respond to noradrenaline and adrenaline to increase inotropy and chronotropy. Both adrenaline and noradrenaline contain an aromatic ring with 2 phenol groups. These make hydrogen bonds with 2 serine amino acids in the active site. All beta blockers contain this aromatic ring to fit into the active site, but without the phenol groups, thus avoiding activation. Proximal to this aromatic ring is an oxypropanylamine derivative.
In other words, it is a propane chain with a hydroxyl group, an ether group, and an amine group. The ether and hydroxyl group make hydrogen bonds to amino acid residues
surrounding the active site, whilst the amine group forms an ionic bond with a specific aspartic acid residue. This is nicknamed the ionic lock that keeps the beta blocker in place. Distal to the aromatic ring is a polar group, which can either be an amide, ester, or ether. Amides are the most polar functional groups, since the lone pair of electrons on the nitrogen atom shifts towards the oxygen atom. The edge of the active site is known to possess polar amino acids, including lysine, histidine, and tyrosine. These also make hydrogen bonds with the polar group, reinforcing the binding. This distal group also helps influence the cardioselectivity of these drugs. Beta-2 receptors exist in the lungs and blood vessels, and beta blockers can activate these receptors too. The bulkiness of these polar groups reduces their ability to slot into the narrow beta-2 receptors. This is why bisoprolol has the highest cardioselectivity compared to these other common beta blockers. Unfortunately, no beta blocker is entirely cardioselective, which explains unwanted side effects on blood pressure and breathing. As an alternative, we can use calcium channel blockers. Calcium channels are what mediate muscular contraction and the heart's pacemaker activity. Thus, blocking them also brings about a reduction in inotropy and chronotropy, respectively. Calcium channels also mediate the muscular contraction of blood vessels, so unfortunately, there is still not a complete cardioselectivity with these drugs. All calcium channels are made of 5 large protein subunits. The alpha-1 subunit is the central pore that lets calcium ions in. This subunit is composed of 4 smaller repeating sections called motifs. Each motif is made up of 6 smaller units. Units 1 to 4 lie on the outside of the motif and form the voltage sensing domain, whilst units 5 and 6 lie on the inner side and form the actual pore. It is at these 2 units that the calcium channel blockers bind to. The 2 most common calcium channel blockers are called verapamil and diltiazem, with verapamil being the more cardioselective of the 2. Verapamil is a phenylalkyl amine derivative. Phenylalkyl amines are tertiary amines connected to 2 phenyl groups. Verapamil exists as a salt with hydrochloric acid, but when it reaches the heart, the amine group deprotonates to become neutral. This allows it to pass freely across the membrane. It then reprotonates and binds to the channel from the inside. The drug adopts a folded conformation such that the amine group faces upwards towards the extracellular side, whilst the aromatic rings point downwards. The protonated amine group forms electrostatic forces of attraction to units 5 and 6 of each motif. Specifically, it binds to a region called the P-loop, an amino acid chain connecting units 5 and 6. This chain contains glutamate and aspartic acid, which are negatively charged and thus attract to the positively charged amine. The meta-methoxy groups of each phenyl ring makes a hydrogen bond to tyrosine residues. The nitrile group forms a coordinate bond with its lone pair of electrons to the calcium ion within the channel. This last feature is highly important. A calcium ion in the channel strengthens the bond with verapamil. In other words, verapamil preferentially binds to channels that are activated and open, a property called use dependence. The heart is constantly contracting. Therefore, in comparison to blood vessels, the channels in the heart are more likely to be activated than not. This accounts for verapamil's cardioselectivity, and specifically, its use in arresting abnormally fast heartbeats. Diltiazem is a benzothiazepine derivative. Benzothiazepines are benzene rings attached to a thiazepine, a 7-membered aromatic ring containing 1 nitrogen and 1 sulfur atom. In contrast to verapamil, diltiazem does not cross the cell membrane and enters the pore directly. When it does, the methoxybenzene ring inserts itself into a gap between unit 6 of both motif 3 and motif 4. This makes hydrophobic contacts with nearby amino acids. This contact then pulls the motif together, causing a conformational change that inhibits the protein. This tertiary amine group inserts deep into the rest of the pore, and the ester group is oriented towards the innermost binding site for the calcium ion. Therefore, these additional branches help further sterically inhibit the pore. Finally, it is worth also discussing about nitrates. These drugs are not routinely given following a myocardial infarction, but instead, they help to manage a related condition called angina, which is activity-induced chest pain. This is similarly caused by narrowed atherosclerotic coronary arteries, and nearly 1 in 5 people following a myocardial infarction are found to suffer from angina. Nitrates are converted to nitric oxide in the body, which primarily causes dilation of arteries and veins, thus improving blood flow to the heart and reducing filling of the heart. This transiently relieves the symptoms of angina. The most common form of nitrate drug is nitroglycerin, also known as glycerol trinitrate, or simply GTN. As the name implies, it is a glycerol backbone with a nitrate attached to each alcohol group. GTN is taken either as a sublingual spray or an oral tablet. The nitrates are liberated from GTN within the muscle cells that line the blood vessels. This is either within the mitochondria by an enzyme called ALDH2, or within the endoplasmic reticulum by a family of enzymes called cytochromes P450, or CYPs. In both enzymes, their active sites contain cysteine residues that react with GTN. The sulfhydryl group of the cysteine performs a nucleophilic substitution on one of the nitrate groups, detaching it from the glycerol. A neighbouring cysteine residue performs another nucleophilic attack, but this time on the first sulfhydryl group, therefore forming a disulfide bridge. This releases the nitrite ion as nitrous acid. Nitrous acid is then reduced to nitric oxide by the mitochondrial electron transport chain. Each nitrate ion is liberated one by one, becoming nitrite, nitrous acid, and eventually nitric oxide. This in turn binds to an enzyme called guanylyl cyclase, which causes relaxation of the smooth muscles of the blood vessels, thus causing dilation. The active site of the guanylyl cyclase contains an iron ion chelated by a heme complex and a histidine residue. When nitric oxide enters the active site, it acts as a ligand to the iron using the lone pair of electrons on the nitrogen. This pulls on the iron and the heme complex, pulling it slightly away from the histidine residue, just enough to sever the bond with it. It is also believed a second nitric oxide molecule slots itself in between the displaced histidine and iron, further severing the bond. This induces a conformational change which activates the enzyme.
Whilst not everyone may need GTN, the latest UK guidelines recommends that all other drug classes are taken following an MI. Specifically, a statin, a beta blocker, an ACE inhibitor, and 2 antiplatelets. Or as I like to say, you should take 5 to stay alive.